Welcome to Spring LIB.
The author of this textbook must have a different way of using a graph to answer this question, but I'm going to use a graph as suggested to answer this question, but in a slightly different way. First, let's go back and use the ideal gas law to calculate an equation that relates density to molar mass. As you recall, PV equals nRT. If we were to replace N, the moles of the gas, with the molar mass, or the mass of the gas divided by the molar mass, we can calculate the moles if we know the mass of the gas and we divide it by its molar mass. That's just using molar mass as a conversion factor. And then we'll plug in RT. So if we rearrange this equation, you will notice that molar mass will then be equal to the mass of the gas divided by the volume multiplied by RT divided by P. And I'm separating these out for a reason. Otherwise, it would just be MRT over VP. But I've separated it out so you can notice that the mass of the gas divided by the volume is density. So molar mass is going to be equal to the density of the gas multiplied by R multiplied by T divided by P. Now, in order for this to work, we need to have units of density. Density needs to be in units of kilograms per meter cubed. The units kilograms per meter cubed are the same as grams per milliliter, but we do need to be aware that those are the correct units. Then the R value that we use will be 8.314. It will have units of kilogram meter squared per Kelvin per mole per second squared. So we are using the meters and the meters cubed for volume and kilograms for mass. Temperature needs to be in Kelvin, and pressure then needs to be in Pascal. Then we will get a molar mass in units of kilograms per mole. So if I rearrange this equation using the appropriate units, I will get an equation that looks like this. So now if I were to plot the density as a function of pressure, this would be my slope. The slope will be equal to the molar mass in units of kilograms per mole divided by R with a value of 8.314 divided by T with units of Kelvin. That will only work if the density is in kilograms per meter cubed, or the same numerical value as grams per milliliter, and pressure is in units of Pascal. So this is what I did. I went ahead then and I converted my pressure that was given in atmospheres to a pressure in Pascal. And then I kept the density in the units of grams per liter, which is the same as kilograms per meter cubed. And then I plotted the density as a function, I plotted the density as a function of pressure, the density as a function of pressure. And that's what I have down here. And you'll notice that this is my slope. 2.29 times 10 to the negative 5. So the molar mass is going to be equal to, if this is my slope, and I set that equal to, I set the slope equal to molar mass divided by RT, and rearrange it, then the molar mass will be equal to RT multiplied by the slope. So to get the molar mass in units of kilograms per mole, I need to take my R value at 8.314, multiply it by the temperature. We were told this was 0 degrees Celsius, so 273 Kelvin. Multiply that by my slope, 2.29 times 10 to the negative 5, and I get 0.05197 kilograms per mole, or multiply that by 1,000 and I'll get 51.97 grams per mole. So this is part A. Part B says, why is density divided by pressure not a constant as a function of pressure? Well, I plotted that too. The density divided by pressure versus pressure. So obviously you can see that the density divided by pressure is increasing with an increase in pressure. Or it's a linear function. The density divided by the pressure is a linear function of pressure. Why this is occurring is because we are using the ideal gas law here, which suggests that the pressure is a linear function of density and vice versa, but gases do not behave ideally, and so we are going to see some variation. So as the pressure increases, the density will also increase, but not in a linear fashion as suggested by the ideal gas law. But what is a linear relationship is the density divided by the pressure as a function of pressure.